thermodynamics and geometry, which is relevant to how biomolecules interact with surfaces. And he's going to tell us some fundamental results that he's had from his recent thesis.
Thank you, and thank you for giving me the possibility of presenting my work here. Well, the title is Observation of Proteins Linking Thermodynamics to Geometry, and as you mentioned, it is part of my PhD thesis, which I recently completed, and my supervisor was Professor Dietrich from Stuttgart, and I have been co-working with Roland Roth from Stuttgart also, and Klaus Mecke, who is a professor in Erlangen. Well, just do something. Maybe not be enough to have only the first slide.
Well, there's a chalkboard or a whiteboard.
Yeah, well,
If that doesn't work, no, something happened. But that may not be. Is it PowerPoint or PDF?
it's PDF. So
It's even worse.
I don't see why. So I just start.
I'm not a PC person. If you're a PC person,
Yeah, well, normally.
Well, it's not my laptop, so
What happens if you do this? Okay.
yeah, that's what I tried all the time.
This is also not. So now it's PDF. And if you're ready, you
Maybe I
control
can
it.
just I try to just get
If
out
I
of
control L, then I get out
Oh,
of
yeah.
this. No, but that's just getting out of this.
Yes.
Page down, yes. Page down.
Yeah, I did.
Also doesn't work.
Maybe I just open
That's really strange,
it
right?
again. Then it should do. It's just by transporting it. Oh, now it works.
Yeah, good.
I hope then it also works on the big screen. Okay, yes, so sorry for
No problem.
the delay. Well, okay, so here we go. So just as an introduction, I will use density functional theory for classical fluids as a tool for tackling the problem of protein solvation. I just draw you here the most simple, or yes, model classical fluid, if you like, which is the hard sphere mixture. So it's a mixture of differently sized hard spheres, so spheres which interact only by hard collisions. Of course, a classical fluid can have more complex interactions. The important thing is just that the temperatures are high enough such that quantum effects are not relevant. And on the other hand, I will then apply this tool to the problem of protein solvation, and I will establish the link between the two parts of the talk by the concept of morphological thermodynamics, which will allow us to do a very efficient calculation of solvation-free energies by means of DFT. And in particular, I will use two models for proteins. The first one is the so-called fused spheres model, and the second one is the tube model for proteins. And for these two models, I will apply the technique. So just brief introduction into DFT, density functional theory. As you probably know, this goes back to the 60s and the work of Hohenberg and Kohn, who introduced who invented somehow the DFT for electronic systems, so for quantum systems, and that was then directly afterwards extended to non-zero temperature, and only since the mid-70s the concept has been applied to classical fluids. And the first review article on this stems from the late 70s actually, and the key quantity of DFT is just so the one-body density, or just the density profile, if you like, which is the thermal average of the delta peaks corresponding to the location of the individual particles. So this is just the distribution of particles in equilibrium, and then the functional, the density functional, is this omega here, which is related to the grand potential of the system, and this can be decomposed into several contributions. So the first one is just the ideal gas part, corresponding there to the free energy of the ideal gas. Then there's this so-called excess part of the free energy, which contains all the interactions between particles. So this is the non-trivial part of the story. And then we have here the external potential acting on the particles, and the chemical potential, which then transforms the free energies to the grand potential. And the important property of this functional for computational, for practical purposes, is just the observation that if you take a density distribution which is different from the equilibrium one, and you plug it into the functional, then you end up with a higher value of omega. So you can simply minimize the functional numerically, and then you obtain the equilibrium density profile. But of course, the statistical mechanics, even for the hard spheres in 3 dimensions, is not solved exactly. So so far, everything is exact here, but we cannot find an exact expression for the interaction part of the free energy for most relevant systems. So we need to deal with approximations, and I will show you one particular approximation in a minute. But just before, to make the concept a little more clear, I want to sketch here the important situation for my talk, where I have a solute, which I take to be very simple in this sketch, and then the solvent particles. And within the framework of DFT, the solute just enters into the theory as an external potential acting on the solvent particles, so which basically forbids the particles, the solvent particles, to sit within this region here. And then, so we just take our density functional with the appropriate external potential corresponding to the solute, and then minimize it. And what we obtain is now, of course, an inhomogeneity of the fluid, which gives rise to a density profile which is not flat, but has a maximum here at contact with the solute, and then there is a minimum and these oscillations due to packing effects. And then all the higher order correlations can be obtained from appropriate functional derivatives of the density functional. And in particular, the quantity we are interested in, the Solvation free energy, can of course also be obtained just by plugging in the density profile into the functional and subtracting the value for the flat bulk potential of the flat bulk profile of the solvent with no solute contained. I already told you that, well, the interaction part of the free energy is not known exactly, of course, and there is one very useful approximate theory which I want to introduce very briefly, and which then can be used for our purposes for calculating solvation free energies. And this theory is the so-called FMT, fundamental manner theory, which just approximates the excess free energy functional as an integral of an excess free energy density, which is in the bulk formulation, which I choose here for simplicity, which is just a function of 4 weighted densities. This is, of course, the key, the main approximation which is made here. And these weighted densities, 4, depend on the density of the individual components. So we take a new component fluid. This means we have new different shapes of particles, again hard particles here all the time for this theory, and the weighted densities are then obtained just, for example here, just by weighting the individual densities according to the volume of the respective particle, and then we go down and weight with the surface area and the integral of mean curvature and the integral of Gaussian curvature, which I wrote down here. So the mean curvature is just the mean of the principal curvatures, and the Gaussian curvature is just the product of the principal curvatures. And for all bodies which are topologically equivalent to a sphere, this equals 4 pi. So then this is not a very interesting measure. And then, of course, this n naught is just the total density, particle density in the system, because this is 4 pi always for this kind of bodies. Okay, why is this such an interesting theory? Okay, it is for a hard-body mixture, and it's not so clear at first sight to see how this is related to the situation where we have a solute within a solvent. But the idea is just to take the system solute plus solvent as a binary mixture in a very special limiting case where we have this solute component, if you like, which is hard body B so far, which of course has vanishing density because there's just one solute particle, and then just we take the second component to be the hard sphere solvent. And this allows us then to obtain an analytic expression for the solvation free energy. Yeah, so we just one just knows that, okay, this is nothing but the excess chemical potential of the species B, which is obtained as this partial derivative here, and we have to take, as I mentioned before, the limit of the dilute solute component. And from the shape of the theory, we find this form here for the solvation free energy, which has these coefficients here, which contain only properties of the solvent. So these are the hard spheres which enter in these coefficients, and then the solute enters into the game only via these 4 geometric measures here, which then depend, of course, on the shape of the solute or the conformation of the protein, if you want to apply it to this case. And these coefficients can be identified with different solvent properties. So this one is the pressure, this is then the interfacial tension between the solvent and the solute, and then we have these bending rigidities which couple to the integrals of curvature. And this form, of course, it is much more simple in principle than what I showed you before, where we do the full DFT calculation, obtaining all the profiles in 3 dimensions, and then plugging them back into the functional. And it is called also the morphometric form. I will come back to this form and the properties of this form on the next slide. I just want to lose one more word on these coefficients here, which can be obtained analytically from the underlying FMT. And I just want to show you very briefly the different versions, just to give you somehow the historic background of the theory of the FMTs. So the original FMT goes back to Rosenfeld, who wrote a seminal paper in 1989, where he introduced the concept of this particular set of weighted densities and the underlying equation of status with Perkus-Yevig-1, which unfortunately is not very accurate at high solvent packing fractions. This was then cured, and here we have a link to the previous talk where also it was observed that there were white bears. So in this case, actually, the name goes back to a pub in Bristol where this theory was invented somehow by Roach and co-workers some years ago. This equation of state is much more accurate than the one, the Perkus-Yevig one in the high density regime, and for low densities, of course, it is also more accurate, but unfortunately it has an inconsistency on the level of the pressure, which could be cured only rather recently with the construction of a new equation of state, which is designed particularly for self-consistency, and then there is a corresponding FMT to this equation of state. Well, okay, so this is why I use now this white bear version 2, which has the highest degree of consistency to obtain the results for the thermodynamic of the solvent coefficients, I should rather say. So these are again the pressure, surface tension, and bending rigidities, which I plot here. So the full lines are just the analytic results from the FMT, and then we have also the symbols, which now correspond to full DFT calculations. So we calculate the profile and then we plug them back into the functional, and as I showed you before, we can then obtain the solvation free energy, and we do this for spherical solute for simplicity, and yeah, we can see nice consistency. It is fully consistent for the pressure by construction, and then the surface tension is also very nicely consistent, and the bending rigidities are also much better than it was the case of the previous theories. Well, yeah, so why can I just use a spherical solute here to obtain the solvent coefficients? Well, this is the nice thing about the morphometric form, that in principle the coefficients just contain the properties of the solvent and the thermodynamic state of the solvent, so the temperature and the chemical potential, but they should be independent of the solute shape. This means independent of the protein conformation. And here we can make the connection with Hartwig's theorem from integral geometry, which states that every motion invariant continuous and additive function of phi defined on the closed and bounded sets of R3 is a linear combination of these four geometric measures with constant coefficients. And this is important, that the coefficients are constant and do not depend on the solute shape. Well, to which extent is this are the assumptions of this theorem true? Well, motion invariance, this is not no problem. It will not affect the solvation energy whether we turn the protein or move it in the bulk fluid somewhere, and continuity is also not a problem, because if you just change the solute size a little bit, the solvation free energy will not change a lot. Then there's this additivity, which I mentioned here, and this, to make it more precise, would imply that the solvation free energy of the union of two bodies is just the sum of the individual solvation free energies minus the solvation free energy of the intersection. And this, of course, is not obvious that it is always true, and we will see that it is actually not true in all the cases. The good news first, it has been shown that this morphometric form is very accurate for convex solutes, and this has been shown again for the case of hard sphere solvents, but also meanwhile for more complex solvents. And well, but I will show you two examples where we can see the limits of the theory, and this is always when we have to deal with non-convex sets, so with non-convex solutes. For example, this case of the so-called depletion interaction, which can actually be measured in colloidal systems, for example, where we have now two solid spheres which are immersed in the solvent of smaller spheres, and then although all these particles may have purely repulsive interactions, so maybe, for example, hard bodies, there will be a net attraction between these two solutes, and this is simply due to solvent entropy, because there is this depletion zone around the solutes where the centers of the solvent spheres cannot enter, and so it is energetically favorably that there is overlap of these depletion zones which then means that we have a higher solvent entropy because there's more room accessible for the solvent due to the overlap. Well, and in this case, additivity would just mean, well, we have the intersection of the two spheres, which is an empty set. So the solvation free energy of the two spheres would be just 2 times the solvation free energy of a single sphere, which then means, of course, that we do not have any solvent mediated interaction with the morphometric approach. But fortunately, the situation is not that bad, because I didn't tell you that we have to calculate the geometric measures not with respect to the physical surface of the solute, if you like, but with respect to the solvent accessible surface, which I draw here in blue, and which is just shifted by 1 solvent radius from the physical surface. And for these solvent accessible surfaces, we have indeed an overlap here, and we can see that only in the case where the distance becomes 2 times the solvent radius, these 2 solvent accessible surfaces will disconnect, and only then the solvation, solvent induced interaction will be 0 within the morphometric approach. So we can see this here very nicely. This is the depletion potential between the two spheres. We can see the attraction here in this regime. Then there is an energy barrier, and the full DFT calculation now shows us here the oscillation due to packing effects, while morphometry agrees very nicely, and this was a surprise also to many experts in this field, almost until the point where the 2 solvent accessible surfaces would disconnect, but then there is this even discontinuity due to the change of topology of the solvent accessible surface, and beyond this is always 0. I want to mention one more thing, because I was talking about non-convex sets, so it's important to make clear that we have here, of course, a non-convex, a strongly concave part even of the solvent accessible surface, which gets more and more pronounced, if you like, as the distance of the spheres become larger and larger. So again, this failure of the morphometry can be linked with strongly concave domains. And the second example is just a hard sphere fluid in a cylindrical pore. And again, I have drawn the physical wall of the pore, the solvent accessible surface, which then at some point disappears as the pore is decreased in size. And then, of course, if it has disappeared, this means that no solvent sphere fits into the pore anymore. And then, of course, we see that this surface becomes more and more concave when it is seen from the perspective of the solvent. And we see now the surface tension for this pore, for the fluid in the pore, and we see that it has these oscillations here again for narrow pores, which are due to packing effects of the solvent, and we can see that it is a straight line with morphometry. But we can also see that the general trend is well captured, and the deviation relative to the value of gamma is not really strong. And I will show you now that one should keep these limitations in mind, but still the concept of morphometry is very successful when applied to the proteins in the different models, which I will do now. Well, the first model is, as I mentioned in the beginning, the fused spheres model for proteins. So we just draw all the atoms with their van der Waals radii. This is now for a particular protein, the protein G. And again, I have to stress that we do not use the geometric measures of the van der Waals surface, but again, we have to use the solvent accessible surface, which makes of course, the computation is a little bit more involved, but still it is rather easy to obtain these geometric measures. Yeah?
What then is the meaning of the solvent surface tension in such a picture?
You mean for the pore?
Yeah.
Yeah, you just subtract the volume part of the grand potential. Yeah. So this. It's maybe not the best term for that. Yeah. Well, okay, we have to use again the solvent accessible surface here, and so as I mentioned, it's not so complicated to calculate the geometric measures. For a single sphere, this is of course all known, very easy, and for two spheres, things get a little bit more involved, but not really complicated, because we have two additional line contributions, one to the integral of mean curvature and another one to the integral of Gaussian curvature from this intersection line. And for three spheres, it's even a little one more contribution, which is an additional point contribution from this intersection point here, which then adds to the integral of Gaussian curvature. But so it's not really difficult to compute these geometric measures. I show you here results. Now, the full theory or the complicated theory is not DFT, but a related technique. These are 3D integral equations with the HNC, so hyperkinetic chain closure, but the details are not important now. It's just that they took 600 structures of the protein G, which were obtained as local energy, as minima of local minima of the energy landscape of the protein G from computer simulations, and so they used their 3D calculations for these structures. This takes a lot of computational time, but finally they obtained, well, that not surprisingly, the solvative energy increases with increasing radius of gyration. Now, what was the nice finding in this work here of Roth and co-workers is that they can also compute the solvative energies using the concept of morphometry, and they obtain a very nice agreement between the two results. So the deviation between the two values is always clearly below 1%, and the computation is much faster. So it's a factor of by 4 magnitudes smaller. So this is very was a very nice finding, and they have now also done calculations for more complex solvents with attractions, so models for water, and they can even use their method to identify among such a set of structure the ground state, so the real fold of the protein in question. Okay, now I come to the second model, which is the so-called tube model, which goes back to the work of Barnaba and Maritain, who just stated, well, we can model a protein as a tube with a finite radius, which takes account of the fact that the protein needs room to accommodate the amino acid side chains, and on the other hand, they introduce an attraction between different parts of the tubes just to model the effect of hydrophobicity, so that the protein tries to adopt a compact conformation due to its tendency, or the tendency of certain amino acids to shy away from water. So it was somehow an indirect way of including the solvent here. And what they find then, if they have a small tube radius compared to the range of attraction, they find a compact, highly degenerate phase here, which did not display any interesting structure. And on the other hand, for large tube thickness compared to the range of attraction. They find just a swollen face, which is also not interesting from the point of view of structure. But in between that, in what they call the twilight zone, they find now in their Monte Carlo simulations for this model structures which are very similar to those found in real proteins. So the first row, these are structures of real proteins, and they also find equivalents in their model. So the helices here, the hairpin, and the sheet-like structures.
So is the tube thickness then somewhat like a bending rigidity of a rod? I.e.,
well,
it's
the
essentially
tube
like
thickness means that you cannot bend the tube with a radius of curvature which is smaller than the tube radius. So in this sense, it acts like a bending rigidity. Yes. Okay, and this was just the start of this tube model, and then people thought that it would be nice to include the solvent now directly, which was done a few years ago by Sneer and Kenyon. They used the so-called Asakura-Osawa model. So although it's not probably not the term used in this context, they use hard sphere solvent, but they neglect the interactions between the different hard spheres. So this means they consider a very dilute solvent and just consider interactions between the hard spheres and the hard tube. And this then means that they obtain the solvation-free energy just as a term proportional to the extruded volume, which is drawn here in green. And then there's of course advantages for the protein to maximize the overlap of this depleted zone here. And what they found is that if you plot here the ratio, pitch to radius ratio of the helix structure, which minimizes the solvation-free energy, they find that this ratio is large for small solvent particles, and then with increasing solvent particle size, it decreases, which means that the radius of the helix increases, and that was interpreted as a kind of unwinding transition here. And they stated that, well, if we increase the radius of the solvent further and further, we will somehow drift towards a planar configuration, so a bitter sheet-like conformation, because if the helix radius is large, we see locally just a flat structure. Well, and we thought that it was not a good idea to neglect the interactions between the solvent particles, because in general, of course, the protein is not in a very dilute environment, and we wanted to use the morphometric approach to make extend their calculations to the case of solvents at higher densities.
You just said that generally the protein is not in a very dilute environment, in which case you're speaking of the solvent as being not dilute, but of course protein is actually never a protein is always, or at least not always, we usually consider it in a solvent.
Yes.
Okay, so you were being kind, or with your statement about generally it's not usually in a dilute environment.
Okay, so
but you were speaking of in this case, the diluteness of the solvent, which is with the assumption of their model, which is that
they just do not care about whether their results are realistic or not. They just say, okay, let's interact. Let's neglect the interactions between the solvent particles, and in some cases this might be justified. So we thought that it would just be more careful to use the whole set of parameters which we need according to the
Okay, I'm just trying to think of a situation in which that is true. that the interactions between the solvents are can be neglected or
Crystals.
sorry.
Only a small number of solvent atoms or molecules. If you take a protein crystal, for instance.
Oh, of course, but not in solution.
Not in
Yeah.
So then, of
Yeah.
course, protein interactions become very important.
No.
Okay, so let's define now the model, the parameters of the model which we use. So we have for this hard tube now, if it assumes a helical conformations, conformation, we have the pitch and the radius of the helix, which are characteristic. Then, of course, the tube radius is important, and the radius of the solvent particles. And again, as before, we use the solvent accessible surface, which is again parallel at distance r. And this surface is now a little more complicated than the original one of this helical tube, because it shows self-intersection of adjacent turns, and this gives rise to an intersection line, which has again which again makes contributions to the integrals of curvatures. But these calculations can be performed not analytically anymore, but numerical. Before I come to my results, I briefly want to introduce the set of so-called close-packed helices. If we start here on the right side with a large radius of the helix, and we want to obtain a compact conformation, we have to minimize the pitch of the helix such that neighboring turns get into contact. So this is the so-called turn-to-turn distance limited regime. While on the other hand, if we decrease the radius of the helix further and further while keeping the pitch minimal, there comes a point where further decrease of the radius would cause the tube to bend so strongly locally that it would self-intersect, to bend so strongly that it would self-intersect locally, and then we are in the curvature limited regime where we have to increase the pitch again compared to the turn distance limited regime. In between, there is the so-called optimal helix conformation, which separates the two regimes, and this has a pitch to radius ratio which is very similar to those found in actual proteins, and it is termed the optimal helix because it has been found in packing problems also. And so this is what we will refer to in the following as our helical conformation. And on the other hand, if we want to imagine something which is still out here somewhere, where the radius of the helix becomes very large, then we are again in the limit of a quasi-planar geometry, where locally this helix looks like simply tubes which lie in parallel, and so the limit RH to infinity corresponds to a beta sheet-like conformation in this model. Well, the results now for the geometric measures. Here I plot the volume, the surface area, and the integral of mean curvature. The integral of Gaussian curvature vanishes in the given geometry, and I subtract the value for the beta sheet, so which is this asymptotic value out here for large radius RH of the helix. And what we find is that in the case of small solvent particles here, the red curves, we have a minimum of these curves at RH star, which was the optimal helix conformation, and then for slightly larger solvent particles, we find a kink which appears in the surface area and which is reflected here in this jump on the level of the integral of mean curvature, and this shows us that we have a topologic transition at this point here, where we have left to the kink a topology which is equivalent to a solid cylinder, meaning that solvent particles cannot enter the tube which is formed, or the pore which is formed by the helical tube conformation, while on the right side of this kink, we have a wide helix where solvent particles can enter. Now, for even larger solvent particles, we find a minimum which appears here on the level of the volume, and this minimum moves then to larger radii of the helix, RH. And this was what Sneer and Kenyon found and what they interpreted as, so they took the Alakura-Osawa model, which means that they can basically interpret these curves as solvation-free energies, because in their model it's simply the solvation-free energy is just proportional to the volume, and so they stated that, well, with increasing solvent particle size, the conformation with the lowest solvation-free energy will be a helix with wider and wider radius. But if we now draw the complete picture, where we use the morphometric form, which has these solvent coefficients now, not only the first term as Sneer and Kenyon, but also the surface coefficient and the surface area coefficient, and the contributions proportional to the integrals of curvature, we find the following result for the structures which minimize the solvation-free energy as a function of the solvent condition, and the solvent condition for the hard sphere solvent is determined by the packing fraction, which I show on this axis, and the solvent particle size. In the limit eta to 0, which is this line here, we recover the results of Sneer and Kenyon, which means that for small solvent particles we find that the optimal helix has the lowest solvation-free energy, and then we have this unwinding transition here, and we have this unwound helix, this wider helix in the regime of larger solvent particles. But what we also find is that the area of bitter sheet-like conformations is not found at all somewhere here in the phase diagram, but it is at the completely opposite side, namely at large solvent packing fractions and small solvent particle size. And this, of course, is completely different from which was expected, and it is even more striking if we consider, for example, the free energy curve for this point here, where we can see the minimum of the unwound helix, but which is suppressed by the surface contribution mainly, which gives rise to this energy barrier separating even the unwound helix conformation from the bitter sheet conformation, which is somewhere out here. So we can really say that there is no gradual drift towards the bitter sheet-like conformation for increasing the solvent particle size. Okay, now do I have some more minutes?
Mm-hmm.
Yeah. Okay, good. So then I will come now to an example where I have a solvent which has more complex structure than just the hard spheres. So this is now a solvent with a hard sphere core and short-range attraction of strength epsilon square well, so it is a square well potential actually, and we can plot now the solvent coefficients as a function of the attraction between the solvent particles, and what we find from DFT calculations is that the pressure decreases, of course, with increasing attraction between the solvent particles. The surface tension also, the pressure decreases, the surface tension increases. Here it is for the hard spheres at a hard wall, it's favorable to be close to the wall, while of course for a solvent which has intermolecular attraction, it is energetically costly to have a hard wall in the system. So this makes this change of sign here. And if we just place ourselves at 0.8 of attraction between the solvent particles, we can then see on the right-hand side what happens if we add now, in addition, a potential which acts between the wall and the solvent, so the protein and the solvent, and this is a short-ranged potential which can be either attractive. This is on the right-hand side, so we see if we make it attractive, the surface tension gets negative again, so the fluid wants to stay close to the wall, while if we have an additional repulsion close to the wall, this does not affect the thermodynamic or the solvent coefficients much, because even the attractive, the solvent with attraction in contact with the neutral wall has retreated to some extent from the wall, such that the additional repulsion will not have a huge effect, simply on is only concerning a rather small amount of solvent. And now we can combine these coefficients for attraction, for attractive and repulsive interaction, to mimic the situation of hydrophobicity and hydrophilicity in the case where we have protein and solvent repulsion. So this would be the case of a hydrophobic setup. We find that the solvation energy is minimal for a wide helix structure, and it is much lower than in the case of the stretched tube. I just plotted the difference here, and this is just for increasing solvent particle size, while on the other hand we can consider the hydrophilic setup, where we see that now the minimum, well, is for the optimal helix structure, but it is, by its value, it is very comparable to the stretched tube. So this means that if we include now an additional bending rigidity into the tube, there would be no indication in this hydrophilic setup to see a compact folded helical state of the protein. So we can, if you like, we can see again the role as, or we can identify the role of hydrophobicity as a driving force for protein folding, because these values are larger than for the hard spheres even, and on the other hand we see that in the hydrophilic case the protein will not fold. So let me come now to summary and to conclude. I have shown you that an efficient calculation of observation free energies is possible via this concept of morphological thermodynamics, which we combine with density functional theory. I have shown you basically examples for the hard sphere solvent, but it can be applied also to more complex solvents, as long as the interaction or the correlation length within the solvent is not too large compared to the solute size. I have talked about the limitations of the theory. These occur for solutes which have strongly concave surfaces. I have shown you two cases where this can happen. The first one was just the case of the depletion interaction between two solute particles, and the second case was of a solvent in a narrow pore. So strong confinement is a limiting case of the theory. I have applied morphometry in the fused sphere model and in the tube model of proteins, and so this one was just a check to show that the method can compete with full DFT or integral equation theories, which are much more costly computationally, and the tube model was examined to show that the unwinding transition has a different nature as previously thought. What can be done in the future? Well, one important thing where the method can be applied is to consider more complex solvent models. Second point is to include internal degrees of freedom, which can be done by using a bending rigidity, which I already mentioned in the context of the hydrophilic protein. And then one might think about including different amino acid sequences, which then would require to partition the tube into hydrophilic and hydrophobic patches, which can then be treated separately with different sets of solvent coefficients. And one other very important extension is the field of proteins which are in a solvent which initially was not a bulk solvent before putting the proteins. This can either be the case of protein folding under confinement, which is an interesting field of study, and of course the case where we have proteins at interfaces like the anti-freeze protein at the ice-water interface, where then one might think of partitioning the surface of the protein into parts which are neighboring the solid and parts which are neighboring the fluid, the liquid. And yeah, then in the second step, if you like, one might think of using also the concept of dynamic density functional theory to model interface growth, or rather, yeah, the influence of a protein sitting at the interface on the growth of the interface. And with this, I would like to conclude, and thank you.
Well, questions?
You mentioned at the beginning about this limitation of strongly concave surfaces. The actual limitation to the topological invariance associated with whether you can map the geometry to something that has the same topology as a sphere. How far have you pushed that? I mean, you know, for example, this wouldn't work in a Klein bottle protein, or you know, so
Yes, you need to explore complicated topologies.
yeah, so for example, you can have something that has the same topology as a sphere in one dimension, as an n sphere in some other dimension, okay? And in fact, it's easier sometimes to work in a higher dimension. For example, the Gauss-Bonnet theorem changes in higher dimensions, and then go back.
Yeah, so the morphometric approach has been used, for example, for porous media. There, of course, the Euler characteristic is an important number. It's not just this boring 4 pi, which we have here, but it, of course, it counts the holes which are present in the medium. So, and there it was used also, yeah, for investigating these topologies of, say, matte shell X-ray data or so, and then it actually turned out that one could use the morphometric approach to describe, for example, how a solvent in this porous matrix would behave. Yeah. So there, this may be a realistic test, because it is still in 3-dimensional space, of the importance of the Euler characteristic, and it has been checked in the work of Mecke and co-workers.
So the other question is, I mean, you mentioned just at the very end about using dynamic DFT, and so dynamic DFT has been in part used for non-classical nucleation theory, to look at nucleation, and this makes a connection between the shape of the most optimally nucleated crystal, say from a supercooled fluid, and morphological thermodynamics. Has that at all been explored by these guys at the White Bear Tavern?
Yeah. So they would like to investigate this in the future. I think they have. There is so far. There is, I think, no work in this context with which uses the concept of morphology, where you would then have to deal with the different facets of the crystal.
So the last question is the real practical connection to some of the messy things that we see in real ice, for example, in which you have a surface which has got some surface charge density, and you have a Debye layer probably next to it. This makes contact with your last calculation, and I didn't quite understand the way in which the solvent interacted with the. I didn't quite understand the difference between hydrophobicity and hydrophilicity in this case. And would you? So that's my problem. But can you make just a simple connection between those two things and a charged surface?
Well, one can think of just modeling a solvent with charged ions in it, and a solute which carries also some charge, and model this via some DFT, which is not so obvious to do because there are currently no really good theories, but one could do, for example, and this has been done, one can do simulations, molecular dynamics simulations of such a solute, a spherical one, so a simple shape, and then one can calculate this solvation-free energies, and it fits rather nicely with the morphometric form, which was not really, maybe not expected by everyone, because it is a much more complicated situation due to this Debye layer which you mentioned, but still it seems to boil down somehow to this 4 simple coefficients, at least for the spheres. One has to check that.
Okay, and the only problem with that is that we can't do MD unambiguously with water because we don't know the potential.
Okay.
Any other questions? So I missed this transition, which you said was not an unbinding transition then. What was it instead then? And you showed the curve which you had this drop, and you associated that, or other people associated that with the unbinding.
You mean?
No, earlier. I think we had this, but earlier still, and earlier still.
Yeah, well, the point is that
Yes,
you mean this?
yes.
Yeah, the helix get wider,
Yeah.
but the increase in radius is still on the scale of the solvent particles always. So it's not really. It's not
Right.
like it will really get flat.
Yeah.
This
Yeah, I
is
see.
the crucial point.
Good. So there's no further questions, and then thank you everyone. And now we have.
Yeah, we have some drinks, which are always good.
Okay.